Now we need to find the work done by a variable force. It means that the force is not constant anymore. Okay, the force can depend on the position on the time. Okay, so in this case, let's consider when the force depends on the position of the body's trajectory. Okay, for Fk here. Then the work done by this variable force can be calculated as following. So let's consider if we have an object, right, it's just moving along the x-axis here from the x1 to the x2. But now this force F, right, it just depends on the position x. Then the trick to solve for this one is we need to discretize, okay, or we just want to separate. We just want to discretize or just want to separate the parts on the trajectory here into the small pieces, like this one. Okay, and let's say that for each position here, right, it's going to be the xi. Let's just define as the xi, and then the distance or the displacement between the crosses elements or the cross separation is equal to delta x. Then we can get that the work done by the force Fx for the displacement equal to delta x here, okay, for the small displacement equal to delta x here, equal to, okay, so let me use as delta w, right, equal to the Fx, which is force, and then times delta x, which is the small displacement. Then the work done by the force F from the x equal to x1 to the x equal to the x2 is just equal to. So now because the force is the scalar quantity, right, then we just sum up, I mean all the force for the displacement here together, okay. Then it's going to be equal to the summation I, right, of the Fxi and then times the delta x here, okay. So I just sum up all the force for the each displacement here together. But then if we just make delta x here tends to the 0, okay, so it's called the infinitesimal interval, delta x is really small. In this case, we can just change the delta x, right, to be what? To be equal to the dx. Remember, you have seen this one already from the one-dimensional motions and the 2 or 3-dimensional motion as well. We can just change from delta x, right, to be the dx. And also, we can just change the summation to be what? Remember? To be the integration, right? To be the integration. So then finally, okay, we can say that the work done by the Fk here, right, W is going to be equal to, okay, we just change the summation to be the integral, right, the integral of the Fx, okay, and then times dx, and that's it. Oops. Okay. So this is the work done, right, by the variable force F. Okay, so just the integral of the Fx and then times the dx. Okay, so let's consider this graph. So let's see that we just make the plot between the Fx, right, as the vertical axis and the position x as the horizontal axis here. So now this force is a constant. Okay, just draw something like this one. So then at the x equal to the x1, right, the force F equal to the Fx1. And then at the x equal to the x2, the force F equal to the Fx2 here. So what is the physical meaning of the integration? Remember, Wait, actually this one I forgot to sub the lower and the upper limit, sorry. Okay, so what is the physical meaning of the integration? Its physical meaning is to find the area under the graph of the fx, right? Where we have the lower bound and the upper bound to be the x1 and then the x2. So then in this case, okay, so let's consider this picture. It means that we need to find the area of this region here. Okay, so this area, okay, let me just write down here. We can get that the area under the fx and the x graph, right, is the work done by the fx, and that's it. Okay, let me take the note here as well. Good. Okay, so now what happened if we have the three-dimensional motions? Okay, what happened if we have the three-dimensional motion? Then we need to just change this equation again, right? Okay, but that's simple. Let's see. The work done by the force, okay, but now this force is with the vector quantity and it just depends on the r, right? And then we need to multiply with the displacement. For the three-dimensional motion, we have the dr, right, as the infinitesimal displacement here, and then the dot product between the f and the dr. We just make the integration, okay, we just make the integration from the position vector r1 to the position vector r2, and that's it. Okay, so this one is going to be the general form of the work done by the force F, right? But now this force F just depending on the position vector r. Okay, so we're going to use this question later in this chapter. Okay, examples. Find an expression of the work done by the force F equal to the negative kx here, okay, where the k is the positive constant, assuming that the object just displaced from the x1 to the x2. Then again, right, we can have the two approach that we can use in this case. We can use this integration, or we can just use the area under the graph. Okay, so let's try to explore this one first. Method 1. Okay, for the method 1, just use equation. Okay, so we said that the work done, right, equal to the integral of the fx. So this f equal to negative kx, and then times the dx, right, from x equal to the x1 to the x equal to the x2. In this case, equal to the minus k, okay, minus k, the integral of the x dx from the x1 to the x2, right, equal to okay, so the integral of the x dx equal to what? is just equal to the x squared and then over 2, right? Just equal to the x squared and then over 2. So now we need to sub from the x1 to the x2. Okay, so then finally we can get the answer to be the minus k, right? And then x2 square minus x1 square and then divided by the 2 here. Okay, and that's it. So this is going to be our answer, right? Actually, you're going to see this relationship later again in this chapter. Now for the approach 2. Okay, for the approach 2, let's use the area under the graph. Okay, let's use the area under the graph here. Then the first of all, let's try to draw the graph. Okay, so let's say that this equal to f to x, right? And this will be the f. We have equation the f equal to the negative kx. So it means that we're gonna have the linear graph, and then the slope, right, must be negative. Okay, let's have the negative slope here. Then the graph should just look like actually, let me just make it bigger. Okay, x and then f, right? And we have yeah, this graph. Okay, so let's say that the x1 is here and this going to be the x2. Okay, we have the x1 and the x2 here. So we said that we just want to find the area, right, under the graph. So in this case, we just want to find this area. Wait, we just want to find the area of this trapezoid, right? Okay, so we just want to find the area of this trapezoid. So how? We can say that the area under the trapezoid, right, is, okay, area under this one is, okay, 1/2 as usual, and then times, okay, I forgot again, let's say that this one, right, we have this one and this one. Okay, so this value equal to negative k x1 and this value equal to, sorry, equal to negative k x2, right? Because we said that the f equal to the negative kx. So if the x equal to the x1, we have the f equal to the negative kx1, and the same for the x2. Okay. Now the area, right, under the trapezoid is equal to what? Equal to the 1/2 and then times the summation between these two sides, right? So it's equal to minus k x1 minus k x2. Okay, and then times the height of the trapezoid equal to the x2 and then minus the x1. So now here we can just simplify, right? Equal to, okay, we can just bring the negative k out of this parenthesis here. Then we can have the negative k over 2. And then x1 plus x2 times the x2 minus the x1. What is this term? Okay, if we switch the position of the x1 and x2, right, we can have the x2 plus the x1 and then multiply with the x2 minus the x1 equal to what? Does it look familiar to you? So it's just equal to the x2 square, right, and then minus the x1 square, and that's it. So now you can see that using these two approaches, right, we can just get the same results here.